not enough time to cover all the nuances and aspects for this topic, and that is why we divided these two webinars. And first of them will be dedicated exactly profiling and performance for the client server architecture solution, and second webinar will be dedicated exactly disaster recovery nuances and building and constructing the big architecture in the cloud, and probably with some nuances for the load balancing exactly. And so we have already 13 participants, so I think it's good time to introduce our main speaker, Sergey Bratus. He's one of our main experts in the performance probably.
French speaking.
Yeah. And he has huge experience on the all level of operating system, in the kernel development, in the client server architecture solution, and in the user mode, in the server part and the client part. And so really investigated and profiled a lot of big solutions, and I think it is good guy and cool guy for sharing your knowledge with his knowledge with you. And so we are ready. Sergey, please.
Yeah. Hi, everybody. I'd like to welcome you all, and I'm really glad that you're here. And thank you, Claudia, for a very kind introduction. I have nothing to add, but from my side, I would like to introduce Claudia for those who never worked with her. She's the person who makes sure that clients are satisfied and that projects are always high quality and meet all deadlines, and everybody understands each other in terms of requirements and etc. And she's real rock star at that.
Enough. Thank you.
Yeah. So let's dive into the topic. So today we are going to talk about cybersecurity software architecture, its caveats and its ways to build things. And let me share the agenda with you. So we'll take a look at the modern approach and classical approach, and just check the pros and cons, and discuss where those are applicable in which situation. Then we'll discuss when performance is most important. Of course, performance basically always is important, but since at some parts, from my experience, there are some places where those are basically crucial and critical and everything else. So we'll discuss tools and methods to increase the performance and ways to do this. And at the end, we'll have some fun cases from the field, or some theoretical popular things that we can discuss, and and basically talk those out. Wanted to say that questions are welcome, and if you have any, don't hesitate and just write them into chat, and we'll pause at some point few times during the webinar just to address those, right? All right, so let's begin. So let's first discuss common cybersecurity way. And so in cybersecurity projects, basically almost all the time are built using some popular patterns, and those patterns include servers that save data, and by server I mean basically the component that each other component knows about. And those servers may not only store the data, but have some policies or some data that needed for other components to do their job. Agents, or they sometimes called agents, or endpoints, those are the guys who actually do the work on the target machines, protecting the user or preventing any internal threats. And it's very common for guys to ask for agentless solutions, but most of the time those agentless solutions basically have the agent, but it's ephemeral, and they just do their job, collect the data, and then go away without installing and persisting themselves on the target machines. And optional in between components, which may be like proxies, some layer that do the balancing or something else. But basically, this is a just regular distributed and mostly client-server systems. So we'll talk about the distributions and about the high load, and we'll start with the modern approach. And I would like to do this in a form of a little tale, just to see how we got here. And so once upon a time, there was a server, and it was working fine, and then it died, and people got bigger server, this called vertical scaling. And vertical scaling didn't work very well because this server died too, and that started the very nice era of distributed systems. People get to install, we call it availability set, basically a few computers that hold each other and provide some guarantees about the availability and data and storage and everything else. And once we got there, the computer, like hardware, started to get cheaper, and we got the ability to actually increase the amount of the actual computer and provide many availability sets, and that is called horizontal scaling. I think probably most of you know this. And when this started to happen, it didn't stop on those machines, because those machines grew their amount, and they started hard to maintain, and people added the containers that had the data for those virtual machines. And in order to grow the ability to save the data, storages were added. And of course, if you add the data storage, you'll add some kind of cache radius or something to increase the latency for those data gets. And of course, since you have many machines, you have load balancers and API gateways that can help you. This system's always kind of hard to maintain and hard to monitor in terms of how healthy those are and which machines are actually working or which not. So we had the monitoring tools and some messaging queues to communicate between those. And this system's pretty quickly start to require some personnel that actually work with them and set up them and develop. And you need to have stuff for working with those servers, guys who actually set up those, guys who write the code for them, security guys who manages access for those components, and sometimes just the guy who knows how this all works together and design things, etc. And this is very good thing to do, basically, because this basically guarantees us a lot of things: high availability, durability, and but like this is so good that first, when I was thinking about this webinar, I thought that I will do the presentation about this type of things and just do like few slides about each of those components. But then I thought that it's very hard to do something if we don't agree on some fundamental things. And as Claudia told, that this webinar probably will have continuation, and also this is very important if you and this will work on the high load systems and everything. So if you have some specific questions about those, we'd like to get information about what's most important for you and what type of communication and builds that you want to hear from us. But now let's question ourselves how often do we actually need this, and do we have any performance guarantees? So according to some experience of the company which Claudia told you about, like many years of customers and cases, we came to conclusion that this wonderful approach where everything is distributed and works basically fine, but it allows people to lose a little bit on some technologies that are used on each individual components. Like, for example, you don't need that much performance anymore, because those horizontal scaling basically approach gives you a little more power for your system to manage many clients and etc. So it comes to the thing where one of the components start to work a little slow, and then since those images basically like often are the same for all servers, they all start work a little slow, and just it never happens like never happens like all systems just started to work slow all of a sudden. It's really step by step, and since the people that work on the images and applications for those servers are basically the same who works on the data layer go slow too, and at some point on some customers, or maybe on all customers, it comes to mind that basically this thing is built pretty nice, but it doesn't give you what you expect from it. So let's talk about the very fundamental things, the performance, the thing that we basically do a lot with different types of setups. And this is performance. So let's talk about the performance. What if one server exists, and when it dies, it's basically enough that, for some cases where just guys comes to machine and boots it up, or adds another one machine, and the thing will just work fine without the fancy architectures, but having the good optimal software. And the question is this ever the case? And from our experience, I made just a little list of when I think this might be the case, or it was the case from our past experience. So when the customer has less than, let's say, 500 employees, but basically you can have any number there that fits you, and it depends on the, we'll discuss it a little later. I mean, like when the target audience have not, doesn't have a lot of endpoints or agents or everything, you don't always want to set up all this durable soft and just throw money for nothing. And it also depends on the data size. If agents send like, for example, you have the agents that collects the data about the current software installed on the system, or latest updates, or how secure your operating system is, and just sends the report once a day, probably you'll have enough storage just from one computer that will cover all your company needs. It happened that on-premise solutions decided to go that way, because if we're talking about the cloud architecture, about AWS or Azure, it's pretty easy to spin up all the servers and etc. But when you set it up all by yourself, especially on the early stage for startups or everything, and you don't have all people that will basically work on that hardware problems and setting them up, this might be the solution for on-premise things. And also the financial aspects, because customers do not rarely look like this, and basically they try to save some money, and this can help. Again, this really works well for the early stages when you actually don't know and don't want to go really all all big and start small and then start to grow. Of course, it requires software to be designed and built that way that it could be scaled if needed later, but later may, come not really soon, and you'll save some finances doing that. And also the result expectation. Again, those that high load setups with different servers actually do give you some guarantees about the high availability and the data durability and everything, but sometimes you build the agents that actually, if they don't see servers, they put everything on some internal cache that stores on the actual agent disks, and the only guarantee that you need from the server, so it would be accessible at least like once a day or something. We have seen those cases, and sometimes this is the case too. So next, we'll basically dive into the question how to improve the performance and how to make applications work fine in basically classical or modern approach, because this is very important in either case. And for now, we have some time just for questions if we have some, and we'll go.
It seems we don't have conflict questions, but I think it's good start of the about fairy tale about growth in client server architecture, and the next part will be related more technical details. So please type your question in our comment chat, and so we will have the section with questions, and so we will collect questions and explain it during.
Yep, correct.
Mm-hmm.
All right, so profiling. One main thing is that we'll actually discuss some tools that will help to profile and to increase the performance of applications. And one main thing is all tools will be useless if we skip the main rule. And what main rule is, you cannot improve what you cannot measure. This is like, we are sometimes really surprised by how often this is the case. And basically, how to measure things that you want to improve, it's the benchmarking. And let's discuss a few main principles, how to do it right and how to do it wrong. We'll start from how to do it right. First of all, we need to have some requirements on our benchmarking when we do this, and those requirements are repeatability, which means that we have to be able to run it multiple times with and get basically the same output. I think it's obvious why, because when we run it multiple times and get every time different output, this whole thing becomes useless and we basically can't measure anything. No impact. This means that basically the benchmark itself, the test that we run, shouldn't impact the actual system that we are measuring, because that will again give us the wrong results, and will not be able to make sure that we actually improving something by measuring at it again. Agree on the precision level. This means that when we are measuring something and when we need to improve something, we need to should make sure that we understand our system. And if we are talking about some system that basically, like, again, sends some data once in an hour or so, and we probably will not measure nanoseconds and try to win those one by one. And if we have the system that has really a lot of agents, like thousands for one server, and those are either sending a lot of information or acquiring rules or informations from the server, then probably we'll be going a little lower and measure nanoseconds and milliseconds and try to win those in the places where we need those. Acceptance, which means that we actually when measuring, we need to accept the bad places as they are, because sometimes when we are trying to measure things and the component that is really hard to rewrite is the worst one, we try to think that, yeah, maybe we improve here and there other components, and then we'll get some better results without actually touching the main guy who's doing, you know, bad job on transferring things or something. So except this looks like, you know, strange, but I've seen it sometimes when you guys just were really afraid of changing the old legacy code or something, and so just they wanted to measure and improve everything else. And and how to do it wrong. Bad time measure. When you measure your things, you have to use the time that is in the same ballpark with your acceptance precision level, and which means, like, if you measuring seconds, like let's say you measure downloading few gigabytes file, you even probably may you know, measure seconds of that. It depends on network, of course, but and if you are measuring something that requires to have nanoseconds precision, you need to be very careful about what timer do you use, and this basically depends a lot of the operating system and the language that you're using, but basically most of those have some mechanism that will allow you to do that. Measure cold starts. This is a very popular bad case when you measure application from the very start, or when it's not warmed up. And I'm telling about, for example, if you are measuring start of .NET, it starts the virtual machine, the loads, the DLLs, and etc. Or if your application has some kind of internal structure that it is initted only when it's first used, and you first use it and measure that time, it will basically create all pointers and allocate objects and set up structures and etc. And this first run will be only once, and on the start part, and you'll probably just will measure not the thing that you want to measure. Small amount of tests. When you're measuring, you want to run your applications really a lot of do a lot of starts, a lot of measuring, like run hundreds of times to understand how function actually works and get the average result of the execution time. Wrong data tests. Of course, this is one more thing, like when let's say your customer says that your application performs slow, and you start to measure those on some random test that could be optimal in your environment and have nothing in common with the things that your customer has. This is the wrong way to do things, because you'll basically will not get any result and just waste a lot of time. And tricky distribution is another one. Is sometimes it happens that like 90% of the time your application runs fine, and then 10% it is performing really much slower than all that other cases. And those are really, this is not how to do it really wrong, but you have to be careful about when you're measuring things and when you use libraries that actually provide you with benchmarking mechanisms. You have to use the histograms, and I'll talk about those later, to actually see the tricky distributions, and those also sometimes in network called tail latencies, which may occur like 1% of all time, but when they occur, they can dramatically degrade all the system and basically abandon the clients. Infrastructure overhead. If you miss that, you are probably on the way where you fix things that are not actually broken. And let's say your customer have the 1 gigabit network and everything works there, and it's slow there, and you have another network, or basically vice versa is even greater example. Like if your setup has gigabit network and your customer works basically on modems, and it still happens, believe it or not, then you probably need to measure not on your environment, but get the same modems or get the net limiter to bring you to the same ballpark where the problem is. So, and general rule basically is to find the bottleneck, which means you need to not only measure the functions of your product, but also understand the impact of the parts of it, because some functions may work with bad algorithms that works on quadratic time and spends a lot of time, but those are separate threads and they don't have any impact on the whole system. And some function may work almost fine and have few milliseconds extra, but those few milliseconds will slow the whole system 50% or something. So you, while measuring, you have to know the basically the idea of your system and how customers use it and which parts are called more than others and called synchronously. And also sometimes it happens just when you don't have the idea where the actual thing is, and it happens also. You can divide the code in half and say, let's have you'll have the like server software and you have the connections, and your server is able to hold only 20 connections, and when 21st comes, the server just crashes. So first you just exclude the connection handler and see if the server is able to hold those connections, and if it is, you just turn on the handlers again and divide those in half and just find the ballpark where the problem is, and then take a closer look at that part. Yeah, so next we'll discuss the actual tools and examples when to and how to measure what. So it's good time to have some questions if we have some.
So guys, if you have questions, you can do raise hand and to ask in voice. Great, Yuri, please.
Yeah. Hi, Sergey. So I have questions. Like maybe I'm wrong, but for me it sounds like profiling is like the second step. Like first of all, you need to know that you have some problem. How do you find that? Like how do you know that? Like you have some metrics on production, or you have some like performance test or something like that? Or
it really depends. It really depends a lot. Those are really like sometimes basically you just know it because customer writes you and he says that everything is so slow I can't work. Sometimes when you write the system, you are confident about, like, if you put some bad code at that place, it will make the whole operating system work slow, and then you just add pre-commit hooks that will do the benchmark and run and check if those values are under under some value that is expectable. And if it's not, your commits or your builds may fail, and that's the other way how you may know it. Or you may know it from the some testing by manual testing or by auto test that you run. So this is like very different places where you can get the initial information about that system is not working optimally. But usually it happens that people just see this basically because the systems have a lot of data and send a lot of information, and they just know that system gets slower, the internet gets slower, that when I open the file or directory, it takes like 10 seconds to open. Those cases are very popular in the field too, especially with the system development.
Okay, thank you.
Okay,
Yeah.
guys, any questions? Since no, so Sergey, I think continue.
All right. Let's discuss tools that basically are used and may be useful for you when you're profiling and benchmarking. And there are a lot of them, and I made a little list, just separating them by the actual appliance. And so those tools may be the common tools, the tools that are used, basically could be used everywhere, tools that are used for kernel and system software programming, tools that used for software that uses the network. And by that I mean the software that actually sends some data over the internet or receives a lot of data, basically using the connection. Software that controls the network, by that I mean the software that interferes with the network channel, basically changing its behavior, maybe measuring or examining it, or doing the impact on some other applications traffic. And of course databases. Those are really separate thing, but we'll talk about those too. So let's start with the common. And by common tools that can help you everywhere, basically, of course, I mean code. You can either do the self-written or benchmarking libs. For self-written, you can basically measure everything what you want by using, as I told before, the timers and special timing tools from different languages. But I prefer using benchmark libs, which are written and have everything, every statistic information built in that I want to have. And there is a lot of those libs, but me myself, I was lately basically working on .NET most of the time. And so my favorite benchmark lib at that language is benchmark.net, which gives you very nice statistic about what you have ran. So when you use that and you add the benchmarking mechanism to your code after the execution, you'll have the many runs of different stages of the execution of program, and you'll see the cold runs measurement, you see the hot runs measurement, you see different workloads results for different variables. And also you'll be able, like in .NET, you'll be able to measure its performance on the different platforms for x86 and x64. And so this is very useful. And after all, you'll have the values that are that basically do the statistics about different runs, which are hundreds and maybe thousands sometimes. And you'll have mean and median and deviation and everything. Those things probably most of the time basically you need the average of basically all runs, which is mean. But sometimes it happens that you look at the other fields and they really are useful to you too. And also the histograms that I was talking about before, they look like this. And when you have those, you'll have the amount of run of the application in some time will be shown in the kind of graph, and you'll be able to see how basically the deviation of the mean works. Sometimes the tail latency looks really good with that, because you'll have only one at sign at some really big time value, and then everything else will run on the much less time. And those are very important, because even if it's okay with you, at least you need to know that they are happening. And also basically this library, I just enjoy it, and I thought that maybe I'll spend 4 slides on that. Basically, it gives you an information in all different formats, like you can have the markdown format, HTML, and everything else. So this is very useful. If you work with .NET, check this out. You'll be probably very satisfied with this. So everything else will work over that layer, because when you are programming, you can implement everything. And let's talk about the kernel and system programming. You always can add something to measure the execution time. But if we are talking about kernel and system programming, sometimes you need something else that is, for example, kernel specific. And those things are KDE prints, debug prints, and output debug prints. And basically from kernel mode, you can use KDE print to see the output from that benchmark libraries that either you wrote or you used in your kernel mode. And this will show you the information live from the kernel mode that you are running, and you'll see the timing. It's pretty precise, and so this will not look really fancy and will not have graphs probably, at least if you will not actually transform this to graph. But if you do kernel development, probably this will look, pretty fine, because you have all needed information that you want to. What about system programming? Almost all operating systems have some kind of performance counters, and those are your best friends in terms of performance and measurements. So in mostly for Linux, we use perf events. They called also perf. You can find those whenever. It's like they're really common all over the internet, and you can find the usage of those. You can basically specify what you are interested in, and those events will be collected with step, in few milliseconds or so, and have the information about calling stacks, about memory and other internal mechanism. Dtrace is kind of the same. So this list will have the things that you can use for actually collecting the performance counters. Perfview and perfcollect is wonderful things for .NET developers who's developing for Linux, because those will collect the performance counter that will be aware of .NET and have some nice information for especially .NET developers. System tap is the one basically used for Fedora if you work with this. But those are basically the same, and they collect the information. And if you output this information in text mode, you'll get something like this. You record the process with some feed and then report it, and you'll see some kind of graphs that will show you the execution time and percents which were spent at some functions during the executions. This looks good when the program is not really complicated, or it's the stack traces are not that deep. But sometimes with this approach, you can get something like this, and this will not be as convenient as it was from the very beginning. And at this point, guys just found out the flame charts, which are wonderful replacement for that text view, and they look like this. This is not a city skyline, but this is the performance view of the execution of your application. And probably if you were profiling and seeing the things, you'll probably seen this. And what this means is basically on the very bottom you see the actual process that runs from the very beginning. And then next layers are basically the call stack for the program execution, and you can right away see where all the time went and which functions took most of it to actually get the things done. And so these are very good, and these flame graphs are very useful tools for profiling. But sometimes you want even more. And again, I recommend one more thing, which called SpeedScope app. This is basically a website, and you can find the source of it, how it actually works, and you can you can run probably your own. And what this does is basically the flame graphs that we were discussing before, but do it in a little different way. So first, just the regular flame graph as from the previous slide, where you see the functions and which they called another functions and spend some time inside it. But sometimes it gets difficult to compare the time spent by some of them, especially when they actually grow a little chaotically. So this basically way provides you to do a different views, which might be very convenient. And so let's see how the left heavy view looks. If you put it left heavy, everything will go to the left side, and basically you'll see right away where the all time was spent if you didn't see this on the previous slide. But my favorite actually is the sandwich view, which is a little different, but especially when you have a flame graph with the sandwich and analyze them both, they give you wonderful result, because the sandwich view has the total execution time and self-execution time. And first of all, you look at what you are interested in. The total execution time means that the function actually the code was inside that function for some time. And self means that this function was actually executing without calling other ones. So it depends on what you actually want to measure. Self is more convenient from my side. I need it more often, because this means that actually this function has some algorithms or some job that actually is taking resources. And as soon as you actually chooses any call of this, on the right side you'll see the actual sandwich. Why it's called sandwich? Because this function will be in the middle. On the top you'll see the colors of it, and on the bottom you see calls of it, and you'll see not only the function and how much it spent somewhere, but also how it came to this phase and which threads actually it was in while doing this. Very convenient thing when you are measuring like who's taking the most time. Sometimes, like we had one wonderful case where we had problems with the file system measurements, and then we just measured and saw using this that most of time was spent in close handle routines, which are not really something that you want to, execute synchronously and wait for this. And as soon as we refactored that thing, it basically worked 2 times faster almost. So next, software that uses the network. Again, one of the most convenient ways to actually measure the latency using code, but sometimes you can use captures. Like this is the screenshot from Wireshark. I think like maybe probably most of you probably have seen this. This thing have the timings and the IP addresses and packets, and you can analyze not only the times and latencies, but also the packet internals and see, which data was sent without actually looking into the code or changing it. It also very handy if customer has problems and it's production and you don't have a lot of time by playing and rebuilding and adding logs and adding some diagnostics information, and just find out the reason right away. Software that controls the network. This is the tricky one, because it may work just fine by itself, but when you actually intercept something or doing something with the network card or the packets or something, you're impacting everybody else, and you need to measure those guys if they have latency problems. And one way is to use the actual Wireshark, of course, but also other way, if you work with browsers, and the really fast way to find out if latency has problems, just to open the Chrome developer tools. Firefox has those too, of course. And this network tab has some wonderful information, like when nowadays when you load the web page, it has basically tens of small requests for each other, frame and component, and you'll see all of those using bars, and you'll have the full list of what is loaded and errors on that. And if you open each of those things, you'll see the time that was spent for doing the initial connection, which the time that was spent for SSL handshake, and very interesting field is TTFB, the green one, which means time to first byte. And this timing includes 1 round trip of latency and the times that server spends to actually send the data back. And for example, if you writing your network proxy or something, the latency will slow down, and this is a very good way to just do the quick check if you messed everything up or not. So sometimes it's you do the system programming, and tools from front-end developers work for you very good too. Also, on the same page, there are few fields that DOM content loaded and load, which is actually the time for loading DOM and loading the full page. Those are like really high level estimate for if the network is working fine or not, because you can do one little change and everything, like this numbers, the DOM content loaded and load can grow with like 5, 6, 10 times, etc. Also, there is like one more page called performance. This will work fine for if you actually do something with the exact page, and because the previous slide, the network actually measures the load of the page, and performance measures the page after it was loaded, and actually the performance after it's already been shown. The same flame graph, everything very interesting, and you can find a lot of information there if you suspect that you have problems with performance over there. And databases. So the databases is a hard nut to crack, and basically from the very beginning, there are a lot of hints and a lot of books, right, that actually tell you how to do this right. And few of those is be smart with your storage, like use multiple disk controllers to avoid bottlenecks, do your RAID configuration in a good way, and provide separate disk for heavily used tables and indexes. Yeah, by the way, by database here, I mean relational database. It's not like for Cassandra and Redis and everything. It's a little different, so just don't get me wrong here. Yeah, separate OLAP and OLTP workloads, which means that analytical excuse me, analytical transactions happens rarely but takes more time, and online transaction processing has happened really often and have small amount of time for execution. So basically, if they work on the same environment, they might interfere with each other, basically making unpredictable the load that they can handle. This is something to be aware of too. Then, of course, indexes, create indexes, rebuild indexes periodically, because if you create and then update and insert in the tables, the indexes become fragmented, and they might not work as well as you expect them to be. And so you need to rebuild them and drop indexes that are not used because they are taking place. Having the disk overhead, and also the insertions and update statements basically can become slower because of that, and many more. So like again, there are like many books stating how to write it and do the great way and work with indexes, right? But the main point is that if you're working with the database or any software, you have to basically profile and evaluate everything, measuring in order to improve it. And with databases, your very good friend is execution plan and actually the statistics of the data. And I have an example from the MSSQL server where you can see the execution plan for the query that you wrote, and you can see the what's happening with your data. Like there are some different icons that can be used here that you can see here, like index seek, it retrieves data from the table via an index that fully corresponds to the data. Index scan basically means that we used index, but it wasn't fully correspond to the data that we were looking at. And you even see the errors. If it's little thin, then thinner it is, less data it has inside it. So basically you have the understanding of what's going on inside your query. And also, for example, MSSQL is nice enough to actually suggest you the index that you might be missing, and you should consider adding this to speed up the actual execution. So this is, again, measuring, improving, measuring again, improving, consider indexes, and see if those work for you, or basically will help you to do the performance without slowing the insertions, updates, and everything else. Do we have any questions now?
Yes, guys, we have the last section related to the next section. We are related with popular cases, and so please collect your question related to technical parts. So you can again raise hand, yes, if you have question right now, or you can type it in our common chat. And so, of course, we have question. Prepared question for the I have, but we would like to have some feedback from your side and to hear your question. Okay, Sergey. So please continue the last section, and because we have only 5 minutes.
Okay. So let's have some maybe fun after those, theoretical slides and things. Maybe it will be a little more funny to see. So let's see the popular cases where we can actually fail, and little hints how to not to. So let's talk about server side. When we build server, probably at some point you'll definitely hear the question, will you support 10K agents or something? We call it 10K problem, which arises at basically at any point on all projects that we were building. And so how to achieve that? The most popular error here is to actually work with the multi-threading environments. And I beg your pardon for next picture, but I couldn't resist myself to actually use it. And when we're talking about the multi-threading, in theory it looks like this, but in practice it becomes really a mess. And so what I wanted to describe is the popular way, the very popular server software worked with this. It's called Nginx, and it's working basically. What it stated is that if we are getting the thread for each connection, and each handler is being executed inside its own thread, we'll get the overhead for switching between threads will be high enough to actually be comparable with the actual time needed to handle the request. Because if we have 10K agents or 10K connections, right, we'll actually have the 10K threads for that. So Nginx said that we'll be inspired by the simultaneous chess game and see that one powerful thread can just play with all this, with all that clients handling their connections. And what they did, they had the master process. They had the master process one that actually handles the connections, and when it handles the connections, it creates the connection socket that actually handles the communication, and just put it in some queue, and it has worker processes that default amount is one worker process per one processor, logical processor, I mean. And but you can customize this, you can run more or less of that, and basically those worker processes go from one connection to each other to another, and get the connection, asks gets the question, sends the packets back, and then put it back to queue, and then go to next one. And it turns out that lowering the amount of the total threads actually increases the performance and put it on the next level, and you can do much more with that architecture. And basically the first one, when you have the thread for each connection, is like, for now it looks like naive approach, right? But basically before the Nginx did it, really a lot of guys were doing that thing, and so something similar happens with different parts of servers too, not only with the connections logic. Caches. At some point when you do the performance and you put the big system with a lot of information going, back and forth, you probably will do the caching for one or another component. And so caches is basically main problem of those, is they hard to validate. And it turns out also, why hard to validate? Because this data that is being kept inside cache is basically stale, right? And you have little choice. Either you'll have a stale data, or on the one hand, and on the other hand, you have the requests that go through cache to the original destination, basically making cache useless, and you have to keep the balance between those. So it's hard to find the balance. It's hard to validate, and to find the idea when to start validating that. Sometimes you need to add another messaging system to just make it just regular producer consumer thing. So and it turns out also that sometimes cache introduce the issues themselves. I think we had a blog post not so long ago that was describing the actual Microsoft, right, Claudia?
Yeah, and exactly in my LinkedIn.
Oh yeah, yeah. So it was like the problem with the Microsoft cache, which has the routine that actually checks if the item should be evicted, and this routine is being initiated on every check, insert, or just any cache operation, and it's being run without any locking. So it is possible for many threads, if you're using the cache from the multi-threaded environment, it's possible for many threads to go in the same direction and to run those eviction checking threads. And basically, and all those threads will check each item in the dictionary, and the dictionary is concurrent dictionary, of course, because it should be thread safe, right? And because of that, those procedures basically they pushing each other, and while those are pushing newcomers come to check because, you know, eviction interval basically elapsed. And it might happen that you have the whole system slowing down just because you wanted to use the cache that is actually making the problem itself. Yeah. So another thing that causes, you know, problems is bad code. And of course, yeah, it's obvious, right? But I couldn't skip it because sometimes it's wrong data structures that are used inappropriately, or just, you know, simple bugs or non-optimal algorithms which are written in rush for, you know, for some shipping or something. Bad design, for example, if the with Nginx design, if it was wrong from the very beginning, then you'll probably won't be able to improve it really much and to get to some level where the server could be really high loaded. It happens. Everybody has seen it, and just fast forward to databases. And I have some funny story about the databases, how we can improve performance in a little tricky way. So the idea is a query performs well most of the time, but as soon as you change the where clause and the predicate value, the same query gets 10 to 30 times slower, right? And this is the database. It's just very simple table which has primary key, just value and a big string. And we insert some data into this table and just measure how quick this query will run. And the simple query actually says that we need to get the values from this table where primary key is basically lower than 3057, and then order it by value. Yeah, so, and this query runs, like if you run a few times, it will show you 6-7 milliseconds, just around that. But what happens if you just change the where clause and just add one more value and make it not 3057 but 3058, and it starts run 30 milliseconds without basically no reason, and it is 5 times slower. But if we add more data to the database, it will get more and more slower again and again. So what happens if you see to the actual execution, you'll see that it gets the data and then it sorts it and then goes to the select, and sort has a little mark right over there. And if we see what's the mark stating, it'll show us the different data, and with that data we'll get the warning about the operator used tempdb to spill data during execution with spill level 1, which means basically that sorting happened not in memory, but we needed to use the temporary database to do the sort for that query. And of course, this means that since the memory operations are much cheaper than operations with the hard drive, then we'll get, now we know where we get the latency from. Let's see if it's true, if we used all the memory and we couldn't get into the memory that was provided by the server to execute our query. And yeah, that's correct, because granted memory and used memory and max used memory are the same, which basically means that we went to using the extra mechanism. In this case, it's temporary database. Yeah, and we'll see the estimated row size like this. There is a lot of information from the from these measurements, but the very important here is estimated number of rows and estimated row size, which gives us some number. And how can we increase it to trick SQL into giving us more memory for executing our query? What if we'll change the query from this to this? Basically, what we did is we changed the type of the third argument from character 2000 to varchar 4050, making the SQL server think that the return result will be bigger, and so it will give us bigger memory for executing the query. And yeah, if we check sort looks fine, no exclamation point, which means that it'll be run in memory. And when we checked estimated row size, it grew up just a little bit, enough for hold the data. And when we execute this thing, it goes back to the 6 millisecond, which are fine for us, and we don't have tail latency anymore. This is just, the problem where SQL queries with sorting will use temporary database to actually do the sorting. It's a very big, and it can be tackled in a very different ways, but I'm just telling you that sometimes when you measure and you can do one little trick and everything will work the way you expect it to. So yeah, I hope you enjoyed this little examples. We have a tag blog where we have a lot of articles and examples that you can visit, and probably it's time for the last questions section. I hope we have some now, right?
You
Do
hope,
we?
yes.
Yeah, sure.
Okay.
I'm always open to discussions.
So guys, please, again, I repeat, and so you can raise your hand and I will unmute you. And I would like to tell you that one of our participants, Alexander, shared with you his blog, and he tried to describe the issue with the Nginx and how to work with the big loading for the server. And so I think it's useful information for all of us, and I think and even Sergey also will investigate these articles.
Yep.
And
yep, sure.
Sergey, and thank you. And I have a question, probably some common question, and for a situation when it's good when everything is well, but we know that sometimes fairy tale came set true, yeah, and we know that in production our servers is dead, yes. And how to handle this situation? What is your recommendation? And so probably yes, and even the best developers can miss something, yes, and we can face with some problem with performance issues. And how you recommend to handle this problem when our server in production, I mean?
Yeah, it's a hard question, and it really depends on the actual architecture that you really have, because if it's some web server that actually goes to the customers use it and it goes down, then you probably need to first do the web page stating that we have some problems to make clear that it's not something that was expected, and maybe spin up another server right away and redirect the traffic or something, and do like this kind of things. If it's a load balanced solution and one of your server just died, well, this is completely different case, and you have probably enough time to basically investigate and see what happens, and because it's already basically backed up, right? So, but yeah, the the most important thing also always is to actually get in and collect all the data that is possible, and to see the this is basically the cases which teach you how logs are important and how the diagnostics information is important, and teaches you how to add special flags or special ways to turn on some extra logging if needed or something, because a few times spending a lot of time on the production server without being able to collect any information basically leaves a big pain, let's put it this way, right? So yeah, collect information, make the actual clients possibly happy, or by running some extra servers, or redirecting them, and then just fix it as soon as possible. So what to say?
Okay, and but anyway, I think we need to add some information on our website. Yes,
yeah,
and,
sure.
about that, guys. So, and as we know, they recently when Microsoft had a problem with it. Yes.
Yeah, this is very first step when you have the clients who doesn't know what happened, right? But by the way, yesterday GitHub had problems that you couldn't push and pull any repositories from it. It was in the evening, and they have this the page stating that we having troubles, and you actually can see which components even have the problems, and it's publicly available page. So this is kind of the way nice guys do this, and the way how you probably should learn to do this too.
Yeah, and the next step, I think it's a step by step. You need to recover each component and in our server, and to try to provide the stability of working of our solution. Sure. Okay, so guys, I hope it was a useful webinar for you, and we are waiting for your feedback. And so it will be interesting for us to know what is topic in the performance, in the building of the solution, client server solution in terms of scaling, yes, and which issues you face it in your experience, and probably we will try to open this question during the next webinar. And so thank you for your time, and we are waiting you on the next webinar.